in that sense, it is a linear transformation.
Okay, I think I know it.
Hi.
May I ask you two questions?
Sure.
The first one, I've got a DSB student who switched from one section into another. Should I send the other GSI the letter of accommodation? Or is the letter of accommodation automatically sent?
I actually don't know. I got all letters.
Okay.
But if it's not hard to you, just send him the name.
I'll send the letter of accommodation under these circumstances. And in what concerns the midterm, which sections are going to be covered?
It's up to today. Up to today. Monday is not going to be covered.
Okay.
And I posted some samples. So if they might ask questions, maybe it's a good idea to look at the samples and do something in class.
Okay, so this is what I should do the next week?
Yeah, probably, yeah.
Both on Monday and Wednesday, right?
Yeah. Okay. And by the way, you probably should cancel Friday class after the midterm. It doesn't make sense to have it.
Okay, I'll cancel the class. Okay, in my case, the class which had taken place before the midterm.
I still think it's okay to cancel it. I don't know. Maybe it's a good idea to make some office hours if they want to ask questions before.
Okay.
Instead, I don't know.
I'll post 2 office hours on Friday.
Okay.
Okay.
Thanks.
Thank you very much.
I will send you an email about this proctoring.
Okay. Thank you. Have a nice weekend.
You too.
I'm not in this class, but I was here earlier. Is there a chance anyone left keys in here? Do you know?
Nobody told me.
Okay.
Last time somebody left headphones and they told me. Nobody
Thank
said.
you
I'm
anyway.
sorry. Oh my.
Woohoo. Okay. Whoa! That's lame. I can't do it, right? Whoa! Okay. Where's it? Okay, so okay. So lecture in a minute. Welcome. Thanks for coming in on Friday. I see those of you who made it. So nice Friday. Okay, so we're going to go over Dijkstra again. We're going to do a direct inductive proof of it. And the idea for Dijkstra is it's really sort of there's sort of a one-liner to a lot of these proofs, or one or two or liner. The one liner here, or the two liner here is that, wait, sorry. Sorry. The one liner for Dijkstra is that, you know the distance to some set S at any point in time. Okay? When you've processed a node, all the nodes you've explored, in some sense, all the vertices you pulled out of the queue, you have the correct distance to. Okay? That's one thing you're supposed to know. And moreover, for everybody else, you know the length of the shortest path to them that only uses nodes in S as intermediate nodes. Okay, so that's what we're going to argue, and that's what I'm going to argue. I think I already told you the basically gist of the other proof, right? That's invariant. The invariant is for all the nodes, you know the shortest path to those vertices using vertices only in S. Now, you can think of that with, we'll talk about it more. Okay? So now when you think about a node that's not in S, there's going to be one of them that's not in S that has the lowest distance label. And that's what comes out of your priority queue. Right? The Dijkstra is pulling out the one whose current label is the lowest. Right? And so now we argue that's correct. Right? Because now we want to say that vertex with the smallest distance label outside of S, not only is that the shortest path to that vertex using nodes only in S, it's essentially, it is the shortest path to that vertex. Okay? So, and then that's why you get to add it to pull it out. When you pull it out of the queue, you add it to the set S of vertices whose distance you know, whose distances are properly labeled. Okay? And now, once you've done that, what do you do once you pull it out of the queue? What do you do when you pull a node out of the queue when you do Dijkstra? You look at all its outgoing edges, and you check the distance labels on their neighbors, and you update them if you found a better path. Right? Because now, once you added V to this set S that you know, now you have a responsibility, right? Okay, you have a responsibility. You have a responsibility to maintain this invariant that for all other vertices, their distance labels correspond to the length of the shortest path through S. They did before, but now you've grown S by 1. So you have to consider paths that go through this node, this vertex. Okay, Bellman Ford is we're going to deal with graphs with negative weights, and we're going to introduce this idea. We're going to call this operation, which we already used many times in Dijkstra, of updating an edge. Okay, we're calling it an update. And what we do is we just look at the edge and we say, look, I don't care. You tell me look at the edge whenever. But I'm going to reset my weight if I see that this edge gives me a lower distance. Right? So either I'm going to keep my old distance, or I'm going to see what would be the distance if I assume that's a distance from S to U, and then I add this much. I know there's a path from whatever the path from S to U. Let's say the path discovered so far has length d of U. There's also a path from S to U, and then to V, from U to V. That's a path from U to V. So I kind of check, what's my current estimate? So maybe du changed at some point. So I check whether my current distance label is smaller than this one. If it isn't, then I update my distance label to this smaller path. Okay? So that's this notion of update. And we're going to show that with negative weights, Dijkstra doesn't work. I'll show you that. And we'll also show you that this particular updating of edges, which is already inherent in Dijkstra, right? That's what you do. What you do is when you process a node, you update all the outgoing edges, right? That's exactly what you do. So that's another way to write Dijkstra. Okay, so here's Dijkstra's algorithm. You see the update procedure here. It's not using min, but it's a long way of doing min. And the runtime was this many inserts and this many deletes. With the binary heap, you can do this. I showed you how to do it in v plus e time. I sketched how to use a heap of different degree. Okay? So some students asked at the end, well, they didn't get that part, and that's because, maybe I did it quickly, but essentially, there's no reason to use a binary tree. You can use a ternary tree or a degree D tree, and you have some trade-offs there in the depth versus the degree. Okay? And so I also sketched that last time. Okay, so Dijkstra, okay. So we know the distance to process nodes. I guess I'm calling it R on this slide. Okay, and what we do is we add the node V that's closest to S. That's sort of our intuition outside of R. That's what we're doing. Every time we have a set R, we've already processed all these nodes. We assume their distances are correct. And now, of all the nodes we haven't processed yet, all the vertices we haven't processed, we look at the one with the lowest label. Now, this particular statement is said, in fact, it's not only saying that it's the one with the lowest label from the algorithm, it's saying it is actually the closest one outside of R to S. It's making a stronger statement, the second line. Add node V, which is closest to S outside of R. Okay? And what we really do is we add whichever one has the lowest distance label. Right? That's what the priority queue is. It pulls out the one with the lowest distance label. Right? This is what this step here does. It deletes min out of all the nodes you have not explored yet, or you have not processed yet. Okay? So the key is the closest node V has a path. Okay, and what U is in R. Okay, that's what we're saying, right? Since V is the closest node not in R, this node U must be in R, right? Does that make sense? Okay, this node U must be in R. That's what we want to do. We want to add this closest node to S outside of R. Okay? So what I want to argue is that whatever the shortest path is, A shortest path, is to V, if V is actually the closest node in slightly... Okay, well, I'm going to try this. This is a mess, but okay. Okay, let me see if I can do this. Okay. Oh, I can't because... Okay, I can draw a circle. Yes. Okay, that's R. Okay, you think of that as R. Okay? Now there's some node V, right? And I have some path. And then you go outside. Okay, this is where it gets messy. Okay? There's some edge that goes back there. So those last two nodes are U and V in this picture. Okay? Now, if that's the closest one outside of R, should this path go through another node outside of R? No. Right? It shouldn't, because if it goes through another node outside of R, right, if actually this was the closest node here, I'm saying this can't happen. You can't go to here and then go to here. Why not? Why can't the path look like that? If V is the closest node outside of this circle to S. Why can't it look like that? Why can't I go through another vertex? Okay, this is because we're using... Yeah, because this vertex here, let's call it V prime, would be closer, right? But I'm using something. I'm using something about the graph or the weights to say that V prime is closer than V, or at least it's no longer larger than V, right? What am I using? What are all the lengths? They're positive, right? So since they're all positive, there might be ties. There might be some edges with zero length. So I meant the one. So if V is V may not. It may be true that the closest the path does go through V prime, but V prime is as close as V, so we will use V prime. Okay, as the closest node outside of R. Okay, so this is so then. Well, now we know that so we would use V prime here. That would be that would be a closer node. Okay, and the path, the shortest path to V, the closest node here, V, which is V prime in this picture. Well, this is a contradiction. Let's just make this thing be 5. So this is a contradiction, and the real picture looks like this. Okay? So now this whole path from S to V is entirely inside of R, except for this last edge. Okay? Okay. So now we have this condition that once we add V to R, we have this picture. Now we have a bigger set R. Okay? And then what do we do? So then we know that D of U is correct by induction, and then this length you added. Okay? So that's why you computed this shortest path correctly, the length of the shortest path correctly. Okay? And then now, D of U corresponds to the length of the shortest path. Okay, so and D of V is less than or equal to D of U plus L of UV, because we have a path from to U. We know the path from U, and we know it's this, right? Since U was processed by the algorithm. So D of V corresponds to the length of the path. Right? Now I have a path. It corresponds to the length of this path. Okay, and now it's set by some U, which this D of V, it was infinity first, right? You started with everybody being infinity. And you only decrease the weights when you have an edge to U that tells you to bring it down, right? It's an update. Okay? So it corresponds, so it's set by some vertex, U, which corresponds to a path by induction, plus an edge, U prime to V prime. Okay? So to U prime to V. So whatever this is, the path I have is, the length of this path is at most D of U plus L of UV, where this is the shortest path through S. And whatever, I might have computed, all this is dealing with is the fact I might have computed a different shortest path. Okay? There might be a different reason that this guy's label was set to what it was. Okay? Okay, thus when V is added, D of V is correct. So it corresponds to the length of the shortest path. Okay? Okay, so now what you do next is you update all your outgoing neighbors to get back the condition that for every node outside of R, the distance label corresponds to the distance through R. So you have old paths that went through R, and now you have a new possibility. You have a path that could go through V and then use one edge to U. And that's what the updater's doing. That's why you process the edges. Okay? Okay. Okay, so if you have a negative edges here, this argument totally breaks. Okay? So let's look at this example. Let's just run Dijkstra on this example. Okay? So you process S first. It pulls out of the queue. Okay, and that'll set D of A to be 1, D of B to be 2, and D of C to be 3, right? You process all the outgoing arcs. You have the arc from S to A, which is of length 1, so you set D of A to 1. The arc from S to B is 2, so you set D of B to 2. And the arc from S to C is 3, so you set D of C to 3, right? They were all infinity before. So now, which one is the next thing that comes out of the queue here? You're going to pull something out of the queue. Which one comes out of the queue? A, because it's the lowest one. So you're going to process A. D of A is 1, so it has no outgoing arcs to process, right? No outgoing edges. Then you're going to process B, because that's the next lowest one in the queue, right? We've gotten rid of this. D of A is still set to 1. We already have an arc. We have an arc from B to A, right? And what's that length of that? That's it's 2 plus 0. 2 plus 0, is that bigger or smaller than 1? Bigger. So therefore you leave the label of A alone, right? That's what the update of the edge does. It checks for A. It says, is this new path shorter than the one I already know? Okay? Okay. Wrong way. And then you process C, which is the next one in the queue, and you say D of C equals 3, and it has an outgoing arc to B, where in which case it sets D of B to 0, because it's going to set it's going to look at this new path, which is of length 3 plus negative 3, which is 0. So D of B is 0. Okay? Okay? But I can't, Dijkstra doesn't allow me to process the B again. Okay? Since it doesn't allow me to process B again, D of A is still going to have length 1. But what should be the length, distance to A? Right? You're like, come on, get there. You're going so slow. It's 0. It's clearly a problem. Okay. So the problem was D of B was incorrect when processed. Right? What happened is in this ordering, B was not the closest node to S. Right? We processed B when, in fact, we processed A. We processed A when A was not the closest node to S. B was the closest node to S. But we don't know that yet, right? Because there's this negative edge out there. Okay? So it should be 0. All right. Okay, so this is a basic routine. Whenever you're sort of just searching, and what you do is your labels, you got to think of your labels as, this is the best path I know so far. So think about it as a big, massively mess of a process. Okay? At the very beginning, you know the label to S is 0, is of length 0, and everything else is infinity. Because I have no path to anything else. Okay? So you know this. You have some estimate for the distance to S, which is correct at the beginning. But you don't know the distance to anything else. So that's infinity. And now what you do is you look at S and you look at all its neighbors and you set their distances. Okay? Using update. This is now where we're using this update. Okay? And now this update, what it always does is it changes the distance to something lower. Okay? But does it ever change it to something that's too low? Like less than the distance of any path? No. That's the key with update. Right? We're saying, look, I have my estimated distance, which is some path to me, and there's the estimated distance for you, and these are all upper bounds, right? Now, infinity is an upper bound on the length of the path, right? It can't be any more than infinity. So now I'm saying, well, there's some path to you that this distance u is achieved by, and that now I'm saying I'm always going to take the minimum of whatever path I know already, which is sort of written down. The length of that is written down in distance of v, and this other path that goes through you and then comes to me. Right? There's two paths. I'm always comparing two paths, and then I'm setting myself to the length of this new path. Okay? So it's sort of searching for paths, sort of slowly. That's what update is doing. It's picking the best of a path that we know. So far, we don't know anything about the distances except they correspond to a path. So we know there's a path of length d of u here, and there's a path. We know there's a path of d of v here. Okay, and now we're saying, okay, I know I have this path. Well, is this path shorter? That's the question. If it is shorter, then I reset my weight to d of u plus L of uv. Right? This is L of u of uv. Okay? So this is what update is doing. It's this operation that says, I'm just going to look at an arbitrary edge. Now you can just think of a really stupid algorithm. right? You could just start S with 0, start everybody else with infinity, and just start looking at arbitrary edges. Okay? And if they improve, that's fine. If they don't improve, that's fine too. Right? It doesn't hurt you. You're always going to ensure that you have a path that corresponds to this distance. Okay, this update operation is just very simple, but all it's saying is whatever path you could think of it as, here's an estimate on my path, here's a path that I have this length. Oh, let me check this other path. Okay? That's all you're doing. Okay. So in Dijkstra, you do these things by processing the closest unprocessing nodes and updating the neighbors. That's the algorithm. Okay? Okay, the properties are that D of UV is correct if U is second to last node on the path, and D of U is correct. Right? Okay, so if you update on the last edge in the shortest path and you have the right distance to U, then you have the right distance to V for edge UV. And you never make D of V too small. You're always conservative. You're always only picking from these two possible paths that I drew. Okay, so it doesn't make errors in the sense that it doesn't ever say the path the distance label never gets too small. It always corresponds to some path that you found. Okay, so it's harmless. Okay, so now we have this procedure, this thing. Now we have a shortest path, and you saw that Bellman. This doesn't work for negative edges, but what we could say is, let's think about if it's an arbitrary graph with negative edges, and we say this is the shortest path from S to T. There's some shortest path. Okay? So now I can just start applying the update in whatever order. I can update the edge from U2 to the U3, or edges that aren't in this path, or whatever. Okay, but if at some point, say I update S to U1, I update this edge, will I have the correct distance label on U1? This is the shortest path from S to T. Will I have the correct distance label on U1? I'm asking you to draw a conclusion here. Objection. He's asking for the witness to draw a conclusion. Okay. The conclusion I'm asking you to draw is that every subpath here is also a shortest path. Okay? But that's clear. If it wasn't the shortest path, if there's another shortest path from shorter path from S to U1, then you could find a shorter path from S to T. Okay? Okay, so after you do that, you have the correct distance label on U1. And now if at some point during your algorithm I'm just doing random updates or arbitrary updates in some order, and I update the edge from U1 to U2, will I have the correct label on U2? Will I have the length of the shortest path on D of U2? Will it be correct? Will it be the length of the shortest path? It will be the length of this path. Okay, and so on. So, right? If I could just find a way to update all the edges so that for this path, at some point, I could do all kinds of updates in between, but at some point in the sequence of updates, I updated S to U1, U1 to U2, U3 to U4, and so on, then I would have the correct distance for this path. Right? So how do I set up a sequence of updates? Now, I want to set up a sequence of updates so this particular order happens as a subsequence. Okay? Like I could just try, right? I just want to update all over the place, right? Now I've reduced this problem with just updating edges. Okay? So Bellman-Ford says, well, this is what you do. You just update all the edges, n-1 times. Okay? That's what you do. Okay? And now the first iteration through here, what have you done? Have you updated S to U1? Yeah, you updated all the edges. Right? In the second iteration through here, have you updated U1 to U2? Have you done that after you've done the update for S to U1? Yes, because you did this one in the first iteration. In the second iteration, You also may have updated U1 to U2 in the first iteration, but you may not have done it before you updated S to U1. But now, after you've updated it once, after you've updated all the edges once, you know for sure you updated S to U1. After you updated it twice, you know that for sure you've done S to U1, and then somewhere in the sequence you've updated U1 to U2. Okay? So the correctness is that after the ith loop, D of V is correct for any V with I edges in its shortest path. Right? That's what we're arguing. Right? And it's easy. The base case is it's correct for 0. S, D of S is 0 after you've done no updates. After you've done one round of updates, you know all the vertices who have a length 1 path from S to those vertices, they're correct because U1 here, for example, has a length 1 path from S, their shortest path, a length 1 a hop 1 shortest path, and it's correct. Okay? So it's a fairly easy induction. And it's also fairly easy to argue the runtime, right? You just do this V times, or V minus 1 times, and you update all the edges. Okay? Okay, and then finally, why do you only need to do it V minus 1 times? Why do you only need to do it this many times? What's the largest number of edges in any path, in any simple path? What's the largest number of edges in any simple path of a graph? Well, there's V vertices, so the path can only have V vertices in it, so there must be V minus 1 edges. Okay? And that's the proof for Bellman-Ford. Okay? Okay. So now, okay. So here's an example. I guess this is the one from the book. We can see it. So here's S. S is 0 here. Here it's hard to tell what's going to happen because there's all these negative arcs, right? So the shortest path from S to A, naively it looks like it's 10, but it may not be 10. Why might it not be 10? Uh-oh. Uh-oh. Wait a second. Okay. There's a problem with this example, but let's just run the example and then we'll see what the problem is. Okay. I thought I got it out of the book, but maybe I mislabeled something. Okay. Well, let's see what happens. Okay. So we're going to update all the arcs, right? What does updating this arc do? What we're going to do is reset the label on E to the minimum of its current label to this label plus -1. Oh, this is fine. Actually, I was wrong. This is fine. Okay. Okay, so what would this label still be if I update this arc? Well, infinity minus 1 is just infinity, right? This is weird, but that's what it is, okay? So it's just, you don't change the label, right? For this arc, you don't change the label. It's clear, all these arcs, you don't change the label except for which one? From S to A and S to G. Okay? Okay, so those, their current label is infinity. So if you update the arc from S to A, you reset the label to the minimum of infinity in 10. 0 plus 10. And the same thing for G here, right? Okay. And now we can do this update. We're, again, updating all the arcs. I'm not doing one at a time, right? I'm doing a sweep over all the arcs and seeing what happens. Okay? So here F gets 9. This gets 12 because of what? Why does this get 12? Because the arc from where? A to E. And I think that's the only changes. Okay. Okay, so this one is a couple of more changes. So this gets 10. Oh, yeah. Okay, so what happened is this is 12. Look at B. B gets a minus 2 here. So B gets 10. Okay? That's what's happening. So the reason this looks like it should get something smaller is because this also changed, right? It changed from, this one changed from 12, and then it relaxes this one, right? This arc tells it it should be 8. Okay? And so on. And you can just see it progress. And the thing I was scared about, just to make it clear, is this cycle here looked to me like a negative cycle. But is there a negative cycle here? No. Okay. That's I just panicked for a minute because it takes a long time to make these animations. I thought I made a mistake. Okay, so this is what happens, and so on. And you can see sort of the effect of this as it goes. Okay? Does that make sense? And then when you're all done, I guess the 7th iteration, you're all done. There's 1, 2, 3, 4, 5, 6, 7, 8 nodes. After 7 iterations, it did converge. Okay? So there's one path. And the reason it took that long is there's actually one of these paths is of length 7. Okay? So that's why it took that long. Okay? Okay, so now to be sure you can get lucky. Okay, so now one thing I should say right now is this is like a very simple algorithm, right? It's just really simple. It's not clever at all. It seems not clever at all. And often you want to do better. And in some sense, this is still an open question, in some sense, whether you can do better in the worst case for Bellman-Ford. So this very simple algorithm is, in some sense, the best algorithm we know after many, many years. So it's it's really tempting to think you can do better, and maybe you can. Please go forth and try if you like. But other people have tried a lot. So okay. So now Bellman-Ford, D of V is the length of an I edge shortest path at iteration I. That's the idea. D of V is less than or equal to the length of the I of an I edge shortest path. Okay? So this assumes the length of the shortest path is at most n minus 1. Okay? Why? It's assuming in some sense there's no cycles. I made this argument quickly. I said that, well, the shortest path should be a simple path. It shouldn't have cycles. Okay? Why? The cycles should only add length. That was the intuition. Like if you have a path and you have a cycle along the path, you might as well throw the cycle out, right? Because it should only add length to your system, right? Because if you go around, it takes a while to go around, and it's going to be longer, right? But we have negative arcs here, so that's not necessarily true. Okay, so the cycle doesn't only add length, right? There's this sort of weird thing that happens with negative arcs, right? You saw me panic when I saw a negative cycle. Well, when I missaw a negative cycle. Okay? So it's not necessarily true that this algorithm even works, right? Because this algorithm claims that the length of the shortest path is n minus 1. Okay? So how do you deal with things where you do have negative cycles? Okay? Right? There's a negative cycle. Right? If it's not negative value, you know it's fine. The argument is correct. The shortest path is definitely a simple path. So if there is a negative cycle, in some sense, the whole problem makes no sense. Right? Because now, what's the length of, if there's a negative cycle, what's the length of the shortest path? Well, I go along the path, I go around the cycle once, and then I go on to wherever I want to go. Would it be shorter if I go around the cycle twice? And so it makes it's already a problem, right? Okay? So now I want to say, how do you tell if there, so you just, in some sense you want to say, I want to either compute the shortest path or say this graph has a negative cycle. And I can't really, it doesn't make sense to do so. Okay? So now how do I check if there is a negative cycle? Well, after n iterations, some distance changes, there must be a negative cycle. That's true, right? It's definitely true that if the argument before, if there's no negative cycle after n minus 1 iterations, everybody has their shortest path length. Any update is not going to decrease their shortest path length because any update only corresponds to the shortest path. Okay? So, and you've gotten your distance to be as long as an n minus 1 hop or edge path. Okay? So, but now one more thing, if there's if some distance changes after n, but now you want to argue even more. You must argue that after n iterations, a distance will change. Okay? So you know there's a negative cycle. Maybe it stops for some reason, it doesn't change, but you want to say if there is a negative cycle, if you run it for n iterations, then a distance will change. Okay? Okay, so let's see why. Okay, so let's look at this. This is, let's just do Bellman-Ford. So you relax all the edges. These are all set to infinity. So after one pass over all the edges, this will be 10, B and C will be infinity. After the second pass, what will happen? Right? B will be 15, right? This is not too hard. After the third pass over all the edges? That's 5, right? C will get labeled 5. And then what will the length, then after the third pass, what will happen? Right? That'll become 9, right? And what will B become after the fourth pass? I wonder if I have it here. Yeah, 14. Right? Once you start going around the cycle, will there always be an edge, a vertex that's updated? There's always, as this thing goes around, once you start relaxing the edges on the cycle, it's just going to keep going forever. Right? This should have been 4. I don't know why that popped up there, but it should have been here. Okay? Okay, so that's why if you have a negative cycle, it takes you some time to reach the negative cycle, but once you're on the negative cycle, there's always one vertex whose distance will be updated. Every iteration after that, forever. Right? Because you keep going around the cycle, adding this negative length of the cycle. The negative length of the cycle is -1. So at the head of this process, it will go from 10 here, went down to 9. That will go to 4, 1 less. The next one will go to 1 less. You'll feel the effect of that negative cycle. Okay? Okay, so now finally, we want to look at Dijkstra. It's a directed graph with positive edge lengths. That works well on that. Okay, so it's order m plus n log n time, or a bit better. Okay, so Bellman-Ford is a directed graph with arbitrary edge lengths, okay, including negative ones. And that's order nm time. And now, with arbitrary edge lengths, you could have negative cycles. So Bellman-Ford has to do both. It has to deal with the graphs with negative cycles and say, this graph has a negative cycle. Or it has to, if it has no negative cycle, it has to deliver the shortest paths. Okay, and it can do that, both of those things in order nm time. Okay, so how about directed acyclic graphs? Okay, can they have a negative cycle? They have no cycles, so they can't have a negative cycle. So first of all, for directed acyclic graphs, even with negative edge lengths, you know you have no negative cycles. Okay? Okay, so now, is it possible for it to have a negative cycle? No, because there's no cycles. Right? No cycles at all. So now let's think about a directed acyclic graph, which is a DAG. Remember the Alamo. What? Okay. Remember a linearization. Okay? Remember we linearized DAGs, right? Where we put all the arcs from that we can put them out in an order that go from left to right. And so remember it's an inverse post-ordering number of the depth first search, for example. Okay. Goliad. Is anybody from Texas? Okay, I'm from Texas. So this is a Texas thing. Does anybody know what the Alamo is? Yeah. Yeah. Okay. Yeah, it was a sad thing. It's something to do with war, but it's bad. People were killed. But they teach you this history in Texas. Yeah, The guy, there's a few people in this fort against an army of thousands, and the leader drew a line in the sand and said, any of you guys who want to go, you should go, otherwise you should cross the line. They all crossed the line. They were all killed. So they bought the revolutionary forces some time to get more people. You know, it's a heroic story. It's a hero's tale. It was sad. Okay, so now you should remember that the key here is linearization. So as long as you do this sequence of updates, now you want to think about linearization. Okay, linearization, and you want to think about why Bellman-Ford works. You're just taking a sequence of updates. If you know you're doing the sequence of updates in order along the path, then you're good. Okay? Now, the DAG itself has a linearization where any path goes in order from left to right. Right? So every edge goes from here to here, and then from here to here, and then from here to here. So if you just relax, if you update all the edges in the order of their tails order, they will be updated in order. Okay? So the shortest path on the DAG is just you linearize, and then you process the nodes in the linear order. If you process them in the linear order, you'll get the correct distance for every node when you process them, because all the paths come from before you. Okay? And they've been relaxed inductively in linear order. Okay? Okay, so here's a DAG. This bad example for Dijkstra was a DAG. So, and I've written it as a linearization now. I've written it so that all the arcs go from left to right. And now it's going to work because I know that I'm going to update the edges in the right order, even if I only update each edge once. Right? I'm going to update all the edges from S to outside of S. And it updates and puts all these updates as gets D of C is equal to 3, D of B equals 2, and D of A equals 1. Okay. But that's not the correct distance to A, but it's a distance to A. Okay? Now we're going to process C, which is the next one in the linear order. And then I'm going to update the one arc out, which D of B is 0. And now this was a problem before. Before we processed A first, because it had the lowest number. But now we know that all the paths don't go through A to B, but they do go through B to A. So we're going to process B first. Okay? And once we do that, we can set the distance of A to 0. And that's the correct thing. Okay? And so that's a lecture in a minute, but I went over this a few times. It's Friday, so we should just let you go home. See. Is that yours? Yeah.